to mind time allocated for the presentations and to reserve several minutes for discussions. I will show and indicate 5 minutes at the end of each presentation. Well, okay, the first speaker, Aishin El-Khazali, search for heavy de-boson resonances in electronic final states in proton-proton collisions. Please, 20 minutes.
We don't hear can you please wait a second to adjust everything correctly?
Math.
Okay. Can you speak to see if we can hear you?
Hello, everyone. Can everyone hear me?
Can you do a test to see if we can hear you?
Can you hear me now?
Testing. Can you share your screen? Yes. We can hear you now.
Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay, thank you so much. Sorry for this problem. Today I'm going to serve. I don't know why I'm hearing myself.
Can you hear me now?
Yes, we can hear you.
Okay, I'm going to present a search for heavy de-boson resonance in semi-electronic final state in deep collision at center of mass energy of 30 TeV with the other. So moving to the introduction. So the de-boson searches are highly motivated by many beyond standard model extension and have been proven to be fruitful in the past thanks to Higgs discovery in the particle chart. So since standard model has proven to be a complete theory, many theories beyond standard model that predict the boson resonance attempt to explain some shortness of standard model like dark matter and ERPK masses. So such as extended Higgs detector, extended ghost detector, and quantum gravity. So we are going to present a search for new particles that decay into pairs of W and D boson in the semi-tonic final state, where we have leptonic decay of the boson and the other boson decay hadronically, and this motivated by the nature of leptonic decay, and which also perform better at low masses. And for the hadronical decay, we have a large branch ratio with respect to leptonic decay, and perform better at high mass with guidelines for us. We have three benchmark models: a spin zero random syndrome model called which predicts a particle called radion, and spin one HVT with W prime and Z prime, which are similar to W and Z boson in central model. Is it good now? I don't know how is it now. Is it good?
We can hear you, but we cannot hear you in good quality. Maybe you can at least speak a little bit louder.
What about now? Is it good? Is it good?
It's somewhat better. Yes, you may continue. Sorry for the interruption.
Okay, I was saying that we have three benchmark models: spin zero random syndrome radio, and spin one HVT W prime and Z prime, and a spin two random syndrome gravity. The table here shows the branch ratio and the cross section and the width of the resonance masses for the three benchmark models, and for each benchmark model we have two production modes: GGF Drillian and Victor boson fusion, where we have two quark interferotation with large separation into the rapidity, and have a big invariant mode. For the analysis overview, we are looking for signature of WW or WZ or ZZ resonance with leptonic decay, where one boson decay leptonically, and we can define three leptonic channels: 0 lepton and 1 lepton and 2 lepton, depending on the number of charged lepton in each channel. And the other boson decay hadronically, and depending on the transverse momentum of the boson, we have the resolved regime where the two jets are reconstructed separately as two small R jets, and for the merged regime where the PT of the boson has a great PT momentum, jets are reconstructed as a single large R jet. And for our strategy, we use standard strategy, which we look for excesses above the background in reconstructed the invariant mass of VV or the transverse mass or distribution. And we have deployed new several ideas with respect to 36 inverse bar paper. We have used the Tractable Cluster for large RJ reconstruction and machine learning based GGF to VBF classification. And in this talk, I will cover results from full run to data with three leptonic channel decay. For the object definition, we have the main object of this searches is we have lepton and jet and missing transverse momentum, which is defined as the vectorial sum of the transverse momentum of all calibrated electron, muon, and small r jet, and an associated track. For lepton can be either an electron or muon, and we have two types of lepton: loose and tight. Each one must be greater to 7 and 2 GeV, and must be also isolated from any activity around it, and also the D0 and Z0 significance are shown in table. For small R jet, we use which are a calorimeter-based jet use calorimeter information. For signal jet are required to be in central region of the atlas detector, and for the Victor boson fusion are required to be in forward region. And each one has to have a PT greater than 2 GeV, and GVT must be of 0.59. For large R jet, we use a Tractable Cluster with a radius parameter of 1, and eta must be less than 2, and PT must be greater than 200 GeV with a mass also above of 50 GeV. For the event selection and categorization, for signal region are defined in terms of W or Z mass window, and for the merged regime we have events that pass the mass cut and D2 variable substructure cuts are falling in signal region, and for the resolved regime events only fall in the window mass windows cut are required. For the control region, we have 3 control regions depending for dominant background, W plus Z and Z plus Z and TT bar. For W and Z, control region are defined as same as signal region, but the MGG cut is inversed. And for top control region, we defined is defined as signal region with extra budget required. The schematic, this scheme shows the categorization of each event. We began by selecting the electronic decay, and then we split event into VBF and GGF category, and in each category we defined merge regime which has priority, and then if the event fail the merge regime, it treated in the result regime. For the reconstruction of the hadronically decay in the merged regime, we used what we call Tractable Cluster, which has a new novel algorithm. We use as input tracking information and calorimeter information in order to reconstruct the large RJet. And this has improved significantly both the mass and substructure resolution, D2, and which has give an improvement of 30% in signal sensitivity with respect to the first iteration. And D2 variable is reconstructed by the energy correlation function based on the energy and pairwise angle. And I'm putting here the formula. The right plots are shown the MG as a function of PT and D2 as a function of PT, defining the upper and lower bands for define high and low purity signal region. For the categorization to signal VBF to GGF, we used RNN, which is an architecture able to solve problems which the inputs are a recurrent sequence of information. And for the input variable, we use the quadri-jet momentum PT and the energy and the eta and phi. And for training, we use the signal. The first category is signal that produced by GGF and trillion mechanism. And for the second category is for the VB. And we, of course, we exclude jet from hadronic boson candidate decay. The left plot showed the RNN score, and for the cut on the RNN score, event that has a cut greater than 0.8 are categorized as a VBF event, where the right plot shows the cut efficiency as a function of the mass, and as you can see, RNN perform better for VBF string. And this has been 50% sensitivity for VBF string. For the background estimation, we have the main background, dominant background in all electronic channel decay is the production of the V boson in association with jet. And top quark, both pairs and single top quark. And the boson, which is a non-resonant boson production, and multi-jet, which is a non-resonant QCD multi-jet background. For W and Z plus jet and TT bar, we use data from control region to construct normalization. And for the boson and single top quark background, we rely on theoretical cross-section. For the multi-jet background, we use a data-driven method, in which we derive the multi-jet contribution from a multi-jet enriched region, and we extract the contribution from the distribution of missing ET. Here I'm showing the signal acceptance times efficiency for all the electronic scale, 0 lepton and 1 lepton and 2 lepton, going from the left to the right. For the GGF in the upper plot, and for the lower plot are for the VBF production mode. And as you can see here, differences in the signal acceptance times efficiency are due to primarily to different spin of the resonance mass, and also for the production of each resonance, which is quite different for the HVT and the graviton with respect to the radio. For the here we are showing some data to Monte Carlo plot for 0 lepton and 1 lepton and 2 lepton channel. V plus jet is found to be dominant background in most region, and for the 0 lepton channel we use the transverse mass as the final observable, and for the other leptonic channel we use the invariant mass. As you can see here, the highest local excess is found to be 2.8 sigma in 0 lepton channel. For 1 and 2 lepton channel, data are found to be in agreement with the standard model prediction. For the result of these searches, since no evidence of phoneophysics has been found, upper limits have been set on several benchmark models. Here I'm showing W prime in the left and D prime on the right. So masses up to 4 TV are excluded for W prime, while for Z prime masses up to 3.5 TV are excluded. In the backup you can find more plot for the radio and for the graviton. This brings me to my summary. So we have performed a search for the boson resonance in the forerun to data, and several new ideas and new techniques have been employed, like TCC and machine learning-based signal-to-signal categorization. We have not found any excess, and data were found to be consistent with standard model prediction. And limits have been set on several benchmark models. Here I'm putting the current result on the left table, and the previous on the right table is result shown for previous people. So these new techniques and using more data for run-to data of 1 to 9, the cross section has improved of up to 3 times with respect to 36 inverse bar. Thank you so much for your attention. I'm sorry for the technical issue.
Have a couple of minutes for questions, please. Are there any questions? Please.
For the heavy ones, you could use effective field theory approach. Did you try to do the analysis along these lines?
For this iteration, we didn't perform this, but we are using now AFT for the next round of this analysis.
Okay. So more questions? So probably I will ask. So you have mentioned that there are a variety of different theoretical models that predict the bosons. And is it possible to think about discrimination among these models in the future?
Sorry, I don't understand the question.
So there are different predictions, different theoretical models that predict the bosons decaying to pair of vector bosons. Is it possible to discriminate among these options in the future?
I don't know a lot about that, but for these searches we have used these 3 benchmark models, spin 0 and spin 1, spin 2, but the most significant excess that has been found was for the random syndrome model, which, as I mentioned, is 2.8. HVT is well motivated, of course.
Okay, thank you. Any question? So let's thank the speaker again. And the second talk will be given by Dimitrios Chanko, progress on multi-loop calculations. Please, 20 minutes, including some minutes for discussion.
Can you hear me? Okay, so good evening, everyone. I would like to thank the organizers for organizing this very nice conference and for giving me the opportunity to present part of my collaborators' work. So I will talk about the recent progress that we have made on multi-loop calculation within our group. In the beginning, I will talk about the progress on two-loop amplitudes, and after that, about the progress on the Feynman integrals. Starting with our motivation, despite the fact that many cosmological results indicate the existence of beyond standard model physics, unfortunately, at the moment, there is no striking evidence of new physics. At LHC, this can be found by the comparison of experimental and theoretical predictions. Moreover, the future experiments and the upgrade of LHC will result to even more precise measurements, which will require even more precise theoretical predictions, which can be obtained by using the perturbative QCD. The current frontier on these calculations is the NMLO for 2 to 3 processes, NQBLO for 2 to 2 processes, and N4LO for 2 to 1 processes. Now, as an introduction from the factorization theorem, we know that for the cross-section of two initial hadrons, where is the pointer? This equation holds true, where the hard part cross-section, that NLO, receives contributions from virtual corrections, mixed real virtual corrections, and double real corrections. Now, from these terms, the most difficult to be calculated have been proven to be the two-loop scattering amplitude. Despite its difficulty, in the last years, impressively, there have been some results appearing in the literature for the two-loop 2 to 3 scattering amplitudes, using different approaches for the amplitude reduction. I put here some benchmark references. So for one node to construct and calculate the amplitude, needs to follow the following steps. First, use the standard model Feynman rules and generate all the Feynman graphs that contribute to the process at hand, and collect them to create the amplitude. After that, the integral or an integral reduce the amplitude into a finite set of master integrals, determining the coefficients of the reduction, and finally calculate the master integrals. The final result probably would be of that from here, where Ci are algebraic coefficients obtained by the amplitude reduction and are process dependent, while Fi can be the master integrals of the family, or a special set of functions that depend from kinematics and are process independent. Now let's have a quick review on Helicon loop, which is a program for computing one loop amplitude. So any one loop n particles amplitude can be written in this form here, where ni is the numerator and di are scalar propagators. We can decompose the loop momentum, which lives in 2 dimensions, into a 4-dimensional and an x-dimensional part. And in order to compute the amplitude, we should cast it in this form here, where box, triangle, bubble, and table refer to one loop Feynman integrals with 4, 3, 2, and 1 external legs respectively. R1 is the rational term that originates from the reduction process of a 4-dimensional numerator within the OPP method, and R2 is a rational part that originates by the explicit dependence of the numerator on the echelon dimensions. Now within Helicon loop, the OPP method is used within the it is a method applied in the integrand level for amplitude reduction. The main idea of this method is that for the 4-dimensional part of any numerator, you can write this expression here, where D, C, B, A are the coefficients that we viewed in the previous page, are equal to these coefficients. And the tilde coefficients multiply terms that integrate to 0. So the coefficients are determined by solving this equation by evaluating the numerator for values of the loop momentum where the propagator is advancing, starting from 4 propagators, moving to 3, and so on. Now for the calculation of the 4-dimensional part of the numerator within Helicon loop, we use the Helic program, which efficiently calculates the 3-level amplitudes taken for all possible favor, spin, and color configurations using the standard model couplings and the color connection representation. Within this setup, we use a binary representation for the external particles, which can be viewed as level 1 blobs. The level of the blob increases with the number of particles coming within the blob. For example, this blob here is a level 3 blob. And for the generation of the configurations that contribute to the process at hand, we do a generation of 4 topologically inequivalent partitions of the different level blobs attached to the loop. For example, here for a 6-particle scattering, we have these configurations here, together with other configurations that have a different assignment on the particles of the blobs. So each numerator here is calculated by cutting the propagator between the first and the last blob, which results to an n+2 3-level amplitude, which is calculated without using denominators for the internal loops, for the internal propagators. So this completely automates framework for doing these calculations, the one-loop calculations. After the success of Helic loop, we are currently working on the construction of Helic 2 loop. Our intention is to reuse as much as more from the already working framework of Helic loop, together with new ideas for the amplitude reduction of 2 loops. As in the 1-loop case, for the amplitude of 2 loops at the integrand level, we expect that an expression of this form will hold true, where Fi are the master integrals that will integrate to master integrals, Sj will be the Fourier terms that will integrate to 0, and R1 and R2 are the 2-loop rational terms. In fact, this R2 rational term has been already calculated by a group in Zurich. So in order now to calculate the four-dimensional part of the numerator using the Helicon again, one needs to generate all the two-loop amplitude graphs, again in a block binary representation. For this reason, we have created a generator of all the two-loop graph topologies with master particles within the loop using a list representation. The three ground graph topologies that exist at two-loop graphs are the theta topologies, for which we use this five-list format, the infinity topologies, for which we have this two-list format, and the double topologies, for which we use this five-list format. Now, in fact, we have created two generators, one implemented in Mathematica and one implemented in Fortran. The Mathematica one starts by taking all the possible sets of putting the external particles in the sublist and create the subtopologies by taking all the possible summations of the particles within the same sublist. While the Fortran one, exactly in the opposite way, starts by taking all the possible combinations of putting higher level blobs in the sublist, and then create the higher topologies by splitting the particles, the blobs. In both cases, after the generation, the graph symmetries are applied in order to remove the identical lists. And for both of them, we have checked they have perfect agreement one with another and perfect agreement also with QGraph. But the Fortran one is a lot faster from the Mathematica one for processes with more than 6 particles. As it regards the graph symmetries, the graphs are symmetric on mirror transformation on the vertical and the horizontal axis. All these symmetries can be translated into symmetries of the list using two actions. The swap of two sublists and the reversion of the elements of a sublist. Moving on now to the progress as it regards the Feynman integral calculations. The modern approach for doing these calculations is the differential equation method, within which we define for specific kinematical processes families of Feynman integrals, which are of this form here, where alpha are arbitrary indices, integers, and these are the scalar propagators of the family. Now, the fact that the total derivative vanishes within the dimensional regularization allows us to write this kind of relations, which are called IVP relations, and which imply the existence of finite bases, the master integrals, in terms of which we can write any Feynman integral of the family. Now, the choice of the basis is not unique, and we have a freedom in this choice. So using the IVP relations and the fact that Feynman integrals are functions of the Madison variables, we derive differential equations for them, which we solve iteratively, which we solve in our expansion around epsilon equal to 0, finding first appropriately boundary conditions. And groundbreaking idea that recently has led to the mass calculation of a lot of Feynman integral families is that of the canonical differential equation, according to which if we do a suitable choice of the basis of master integrals, the differential equation will take this form here, which is epsilon factorized, Fuchsian, and the residual matrices are purely numerical, which can be very easily solved iteratively on epsilon. To obtain such a differential equation, the chosen basis should be functions of uniform degree of transcendentality. Unfortunately, until now, there does not exist an algorithmic way to find UT basis or to prove, or even to prove its existence. But there exist different methods that the combination of whom will can lead to a canonical basis. Now, within the simplified differential equation approach, which is a variant of the standard differential equation approach, we calculate the Feynman integrals following the following steps. First, we parameterize external moment by terms of our dimension parameter dx in such a way as to capture the off-cellness of our external leg. Again, here the parameterization is not unique, and different parameterizations are optimal for different problems. Then we take derivatives of the mass integrals with respect to x, and we create for on x a differential equation. And finally, we calculate the boundary conditions for x going to 0. Once with regards to boundaries, first we use boundaries for the already known integrals in closed form or from other already solved families. Then compare the asymptotic regions that are obtained by passing by regions for the mass integrals with the ones obtained by the differential equation using the summation matrix at x equal to 0. We have this relation here. We can obtain a relation between different boundaries of the family. And usually in the end, we are left with some asymptotic regions to calculate, which we do so by doing the integrations in the Feynman parameter representation. As an extra feature of this method, we can take the x going to one limit in order to obtain almost for free the solution of the same family with one external much less. So using the simplified differential equation approach, we have recently computed the two loop matrix Federbox families with one offset leg, which can be described by this Feynman graphs here. These are complicated complicated families with 8 propagators and 3 numerators, and they also have 6 kinematical variables. In order to solve them, we have used this 2x parameterization and a canonical basis. We adapted the canonical basis from this article here, where these families were solved numerically. Results are analytic, and they are expressed in terms of Gonzalez logarithms in the Euclidean region, and we have cross-checked our results numerically with the results of this article here. Also, we have recently calculated analytically the family of the three-loop matrix Federbox with one offset leg, which had been described by this Feynman graph here. Again, this family contains 10 propagators and 5 numerators, but has less kinematics variables. It has only 3. So we use 1x parameterization, this one here. And in order to solve it, we adapted the canonical basis that was used in this article here, where this family was first started. Now, concluding, as it regards the amplitude reduction, currently we are working in order to upgrade the Hela code in such a way that to numerically compute the 4-dimensional part of the numerator from the n+4 3-level amplitude. The next step is to create a general basis of the four master integrals plus Pyrrhus term and the calculation of the R1 rational terms. Now, as it regards the Feynman integrals, we are currently working on the calculation of the 3 hexabox families with one offset massive leg. Again, for these families, we already have a canonical basis from the same group, from this group here, sorry, which recently, last month, they numerically solved these families. And in fact, we have already solved this family analytically, and we are working on these 2 families. And we are also working on the calculation of these 3 loop tensor families with one offset leg, for which we have found the canonical basis for both of them, and we have already solved this family, and we are currently working on the boundary position of this one here. So, thank you very much for your time.
Thank you very much. So the talk is open for questions, please.
No problem.
Thank you very much.
So can you go one slide back?
Yes.
So these 4-point one mass integrals, do they also evaluate to do HPLs or not?
Yes, they also integrate to DPLs, and they have the same letters with the letterbox family.
Okay, all right.
So
That's very interesting.
yes, maybe here also the cluster algebra can be applied for them. The same cluster algebra.
It would be very interesting to check these products of the constant matrices to see if they also vanish, for example.
Yes.
That would be I would be very curious to find out.
We can try this.
Good. And one more general question. So for the one loop reduction, I understood it's important that there exists a general basis independent of the process.
Yes.
How necessary is this also at two loops? Because I think it's quite a stumbling block, and many people have tried to produce a general two loop basis. But
yes, I think until now they haven't. And we are working now by case basis for every process. But it would be useful to have a general basis.
But it's not strictly necessary.
Yes, you can try case by case. Yes, for process.
Okay, thanks.
So, more questions? If not, let's thank the speaker again. Thank you. So, the next speaker, Manuel Frey, asymptotic freedom and higher derivative Young-Mills theories. Please, 20 minutes. Yeah, just half an hour. Yeah. 25 minutes.
Okay. This was the next one, this is the previous one, and this button here is the laser and then pointer.
Okay, thank you. Can you hear me? Okay. So, first page. Let's start thanking the organizers for the invitation to give this talk, especially to George and Guy. We agree that the standard model is very successful from the numerical point of view. We have seen this morning how it survives all possible tests being made. But there is an increasing evidence that this is an effective field theory and requires to be completed. We do not expect that this is the ultimate theory of particle physics. There are many ways of completing the theory. It's a mystery how to complete it and how nature follows one of the completions. But one possible way of doing it, which I will discuss, is just by including higher derivative terms. Most of the completions require to introduce new fields, new interactions, higher order interactions terms, but this particular way of doing is very special. Let's see what are the effects of this completion. This work is motivated by what has been done in the recent years in quantum gravity, conservative approach to quantum gravity based on field theory, local field theory or non-local field theory, which includes higher derivative terms in the classical action of gravity. One of these models, which is particularly successful in explaining scalar tensor ratios in cosmology, coming from Planck satellite data, is the Starobinsky model, which is of this type. It includes higher order terms besides the Einstein term in the gravity. So why this has not been considered so early is because there are a lot of problems with this kind of completions, which usually associated to Gauss causality, a loss of causality and unitarity. This is why this kind of theories has been disregarded since long ago. So let's forget about the massive particles of the standard model and just concentrate in higher derivative terms of the gauge interactions. So in particular, this is the model we shall consider in top of the pure gauge Jamil's term of the standard model. We include a higher order term, which of course it is irrelevant from the field theoretical viewpoint because it breaks conformal invariance and introduce a new scale, which will be large enough to produce the low energy behavior, which is in agreement with the experimental data at low energies, and also has nice properties of the theory at higher energy levels. The term which is here is a very special one. It's a sandwich between two field strength tensors and some differential operator, which is the Hodge Laplacian type. This is the differential form language, but in explicit terms, you can see as ordinary Laplacian and some commutator with a field strength. In particular, if the exponent of this operator is 1, you can see that immediately F-cubed terms appear in this higher ordered completion of the gauge theory. Another nice property of this kind of completing the Jamil theory is that this term in the Euclidean is positive, which is very nice because then you have a stability, at least in the path integral. And also that is so special that because of the choice of the differential operator in between here, all classical solutions of Euclidean field theory associated to Jamils are solutions of the new theory. In particular, instantons are also solutions of this theory. And they are minima in each topological sector of the full action. This doesn't mean that the contribution will be the same as the ordinary theory. It will be different. The bottom of the valley is the same, but the narrow of the valley is different. So the one-loop contributions of instantons will be different. In particular, this will be an interesting question, how the action effective potential is modified when you introduce some theta term here by the inclusion of this term. It will be different from the standard one. And it might be interesting for ASEAN search. Yes? Yes, it is. This is covariant. So this is the major source of problems to keep gauge invariance. Here, you see that this is the covariant Laplacian. So, and this is inside. This is gauge invariant. Absolutely. So, but you are breaking gauge invariance to quantize. You introduce, some gauge phasing, which is very convenient to choose this one for calculations. And then you see that the difference between introducing higher derivative terms in vector like particles or tensor-like particles like gravity is that you cannot get rid of one-loop divergences. For scalars and Simon fields, by introducing higher derivatives, you can get a finite theory. So no need of renormalization. But when you introduce gauge fields or gravity fields, you cannot get rid of this one-loop derivatives. In particular, you can compute for this theory with this gauge phasing what is the two-point function. And it turns out that is divergent. The divergent part is of this type. In dimensional regularization, epsilon is dimensional parameter, standard one, you have a divergent term of this type, where there is a coefficient which depends on n. For n larger than or equal than 2, it has this expression, which is not valid for n equal 1 or n equal 0. They are very special cases which need to be computed independently. For n equal 1, n is the exponent in the sandwich of the Hodge operator. You get this contribution, which does not agree with this one put in n equal 1. And for n equal 0 is just the standard Young-Mills case, which is depending on the alpha parameter for the tuple function. For the other cases, it's independent of alpha. So you need to renormalize at least these one loop divergences for the 2-point functions. There are also divergences in the 3-point functions and 4-point functions. All of them match with this counter term, can be suppressed by adding this counter term, which is proportional to the standard Young-Mills. So this is the nice property of this kind of regularizing this theory with including these higher order terms. Of course, there is a divergent part, but you can fine-tune the renormalization by adding some finite part here, which depends on an arbitrary parameter, which we call it lambda QCD. I mean, this is an arbitrary theory, maybe electroweak part of the standard model, but it's an arbitrary parameter which introduced for convenience. So this parameter, phenomenologically speaking, will be associated to the scale where the low energy behavior becomes asymptotically free. Okay. So doing this, you get you can absorb all divergences in the normalization of the coupling constant, and the beta function, the corresponding beta function, is given by this expression for general group G, capital G. So the coefficient here is what decides which kind of behavior the coupling constant has at the large ultraviolet scales. And it turns out that for n larger than 2, this is given by the previous value I showed you in the previous slide here. Okay, but for n equal 1 or n equal 0, you have different choices. Okay, so the result is that asymptotic freedom for this new theory is only holds for n equals 0, Young-Mills, n equals 1, minimal higher derivative theory, 2, 3, and 4. For n larger than 4, the theory is not asymptotically free. That's the surprise. And if you include matter, you can repeat the calculation. You know that matter always decreases the range of asymptotic freedom. You can suppress some of these values here. But for the standard model case, all of them survive. So only n equal or larger than 5 has this property that the theory in the UV is not asymptotically free. So for these models, which we disregard, you have a strange behavior. The deep infrared, deep ultraviolet, the theory is strongly related. And perturbation theory doesn't hold. So this is why we were only interested in this case. So this means that the completion of gauge theories by including this kind of terms is very much constrained. You have very few models where this theory has UV behavior, just 5 models. The standard one plus these other 4 models. And if you look at the the form factor of the 2-point function, you have this finite part behavior, and you have 2 terms, 1 log of p squared, which depends on this extra scale lambda, and some residual log, which depends on the lambda, which we call QCD-like scale we introduced by hand in the field. The only scale which is at the beginning in the Lagrangian is this one. But we know that in the infrared something will happen, and it's convenient to take care of this with this extra lambda. So the coefficients of this expression are given by the calculation, one calculation, and are of this type for n larger than 2. Of course, there is a alpha dependence here, and they don't have, they vanish for 0, and this one vanishes for n equal 0, and does not for n equal 1. So then you find that you have two UV regimes. One, which is the regime, the deep ultraviolet regime, where T is larger than any scale of the theory, in particular this new scale lambda, which governs the theory. In that case, the beta function, which I will mention, is asymptotically free for n smaller than 5. This behavior, and this behavior for momenta, which are much slower than this scale lambda, and but above the scale which we call lambda QCD. This normalization scheme. So the picture is the following: 2.4 factors has behavior which is logarithmic in momentum, which has common branch here for low energies, and after that point, which is related to the scale, which in this plot we fix it to be much larger than lambda QCD of this order. In this order means that for standard QCD, this new scale is 100 tera-electron volts, which is safe enough to preserve the low energy behavior of this theory. But what happens after that, depending on the theory you consider, you have a different slope of this log plot. And you see what happens, n equal 4 is the last possibility the theory has to be asymptotically free. If you plot here n equal 5, will go up, so no asymptotic free. Well, the next one is n equal 0, and you see what happens. As you increase n, this starts to decrease till n equal 2, but after n equal 2, it starts to increase again, and you get out of the UV ultraviolet asymptotic freedom regime. So the monotonicity of this result is surprising. You can try to enlarge this domain, just modifying this radical choice we mentioned at the beginning of the Hodge Laplace operator, keeping H invariance and never give up H invariance. Instead of that, you can have some other Laplacian, which is essentially the standard Laplacian for a scalar field, for instance, plus some commutator with the field strength, but with an arbitrary parameter here, lambda. Lambda equal 1 is the Hodge case. Lambda different 1, let's see, is a different completion of case series. So you can repeat the calculation. One loop divergences have these coefficients for the beta function, which is depending on n and lambda, so it's more involved. And for, as I said, for n lower than 2, this formula is not longer valid. You have this one, and for n equals 0, you don't have there is no meaning of lambda because this operator does not appear in the diagram. So the plot in this case for analyzing the asymptotic freedom regime is the following. Here you are plotting n, which is the exponent of the Laplacian in the sandwich between two field strengths, and lambda, which is this extra parameter for the commutator with the field strength. So you see that the lambda, lambda equal 1 was the previous case. Here you have n equal 2, n equal 1, n equal 3, n equal 4. N equal 5 you don't have, as I mentioned before. We only consider integer values, one simple reason, because then the Lagrangian becomes local. So n non-integer is non-local, and there might be some analytic problem. So you have 4 theories, as I mentioned, apart from the ordinary Jambi's theory. But if you include the lambda, you have more points here, you know. For instance, but never, you have never n equal 5. For any value of lambda, you never reach 5. So the domain of asymptotically free theories is very much constrained by this, by the one loop physics. So in 4, n equal 4, you have all this range of lambda where asymptotic freedom is preserved. But generically speaking, lambda doesn't help because, you know, if lambda is very large, you are not in the asymptotically free regime. For n equal 3, you have a larger domain, but still, for large enough lambda, you are leaving this. And n equal 2 is a special case. And for n equal 1, you see the same happens. Of course, lambda equal to 0, which is just the scalar Laplacian, which is still gauge invariant, you never have asymptotic freedom. So it's compulsory to have lambda non-zero. I mean, our best choice is lambda equal 1, but you can also the others. What happens here is that if you take lambda large enough, there is only one theory, which is very special and should require some special care, which is n equal 2. These two blue curves reach an asymptotic regime where they touch n equal 2. So, so this is a very special theory. Remember, it was the case where it was the turning point in the asymptotically free domain. In fact, it's the largest one. So this is the situation, and including matter only decreases this domain of asymptotic free. So there are few special points here in the plot, which are the beginning and the end of the asymptotically free regime. These blue points, these blue points for n equal 1 are these two values of lambda, n equal 3, these two values, n equal 4, these two. And as is, I mentioned it, n equal 2, there is only one point lambda. The other one is lambda infinity, as I said, where the two blue curves converge. So these special points for lambda are points where the beta function vanishes. So the theory becomes finite, those special values of the completion of the gauge field. So in these cases, the theory is free of UV divergences. Even at one loop, the theory has no divergences. And the problem is that for none of these values, the instantons, and not only instantons, are null solutions of these Yang-Mills, new modified Yang-Mills equations. But what is worse, the action is not positive for n odd. N equal 1, n equal 3, the action becomes not positive. So we prefer to have this hot thing. So for this reason. So main properties of this completion is that the theorem is gauge invariant, BRS symmetry is preserved, and what is very important for the physics of this model is the fact that in the here I mentioned that the one loop corrections in the case where you have divergences only affect to the coupling constant term here, which is pure Yang-Mills. But this term gets not renormalization, so it's finite. So all corrections to this term are finite. So this means that this term should not change. But since G is renormalized, also lambda is renormalized. And how it is? Well, in opposite way to G. So if G goes to 0 in the UV regime, lambda goes to infinity. And that's fantastic because it means lambda is the mass of the gauge field. So in this renormalization scheme, the mass of the gauge goes to infinity. So it decouples in the UV. So this opens hopes that the unitarity and causality might be restored because of these renormalization properties of the field. And you want to have a more elaborate discussion of this is in the paper, collaboration with Palfetto and Rajwar. I think that this is over. The reception is waiting for us and the concept, but let me just summarize the conclusions. There is something wrong with my slide. I don't know what happened. Well, the first conclusion is that asymptotic freedom is more stringent than we thought at the beginning. I mean, it's very, very stringent condition. Only theories with less than 8 derivatives, extra derivatives, can be UV asymptotically free. All the others are strongly correlated. So even if they are maybe attractive, we don't have tools to analyze it because they go beyond perturbation theory. The nice property is what I mentioned, the mass of the extra gods this high derivatives theory have in this limit go to run to infinity, which opens the possibility of restoring unitarity and causality. And the open question is what if the same things happens in quantum gravity. This is under discussion, and probably similar phenomena occurs in gravity. This will limit the number of models we have to consider, which is a good, for model building, is a good property. So that's all. Thank you very much.
So, again, we have time for questions, please.
Oh, sorry.
I have two questions. One is technical and one is a bit more philosophical. I mean, of course, I agree with you that we need the completion of the standard model, but I'm trying to find out which problems of the standard model this class of extensions could address. I mean, you mentioned the axiom potential, but is there some, so this is my question basically, what could work better than in the standard model in this type of theories? And maybe if I just add my second question, because it will be very easy to answer. You said that in the second half, when you switched on the lambda, the case n equals 0 was somehow excluded, but n equals 0 should be the standard model, right?
Yes.
So how?
No, it's not. No. Let me just first answer to the second question, which is a technical one. It's not n equals 0. It's lambda equals 0. What I said. You know, lambda equals 0. Lambda equals 0 is here. You never enter into the asymptotically free regime.
Then maybe I missed
N equals 0, of course, you have asymptotic freedom. Is underneath here. It's not plotted because it's well known. But in any case, it's not plotted because does not depend on lambda. So it's lambda independent. You know, it's a straight line which spoils the answer. The first question is more important philosophically speaking, as I said. I mean, you remark it. There is one point with the standard model which, from this fundamental viewpoint, is disappointing. This is the fact that the theory is probably not renormalizable in the non-perturbative level. These theories are renormalizable. So, if you think that this renormalizability is important at the non-perturbative level, the reason is that you include the scalars, and the scalars are very bad always. So this is the reason why we motivate this kind of theories. To save the standard model without including new fields.
So for lambda equals 0, it's still gauge invariant?
Still.
It's amazing. And
excuse me, let me ask, because you asked several times the same question.
No. Yeah, it's
this capital D is not is just a covariant square, but a scalar. So the vector index are contracted inside the D, but everything is covariant. This term is covariant. This term is covariant.
Yeah, but I asked about lambda.
This lambda?
No, there's no lambda here.
No, in the other one.
Yeah.
Here. The same. This is covariant. This is covariant.
So there is no cancellation
No.
between those terms. They are separately, I mean, they imply separately gauge invariance for those.
Separately, you could consider, in fact, we started the calculations with just this term. We found that there was no asymptotic freedom. So we got very disappointed. But then we realized that the natural option is this Hodge choice, which is lambda equal 1. And with Hodge, we found these nice 4 cases. And also later on, we include more generic term here, and we find larger domains, which are not much larger, but still some room for different theories. So it's not a problem of gauge invariance. The problem is the dynamics.
And in your very first Lagrangian, when you added those extra term with higher derivatives, I mean, you don't think, I mean, they are again separately gauge invariant.
Of course.
And you could have introduced a coefficient or something.
Yes.
Right? But you don't do it.
No, because, I mean, there are some mathematical reasons why to consider this a natural choice, because everything here are forms. This is the natural operator in forms, and is in the mathematical literature is the one people use. And to pass from here to here is just it's called the Weissenhoff formula, which telling you what is the coefficient lambda here, which is 1 in this case. But this also generalized to higher dimensions and so on, and is a natural mathematical choice. But we found that there are some physical consequences of that, because the larger domain of n is in this with this choice. The 4 theories are only valid for lambda equal 1. If you increase lambda, you are losing powers of n. Perhaps it's a good option go to lambda infinity and to have just one theory, n equal to 2.
Sort of a very nice talk. Could you maybe physically motivate why restrict to this class of gauge invariant terms, higher derivative terms in the Lagrangian?
It's the same question Matthias asked, no?
It was exactly the same.
Yeah, the reason was that the standard model is non-perturbatively non-renormalizable. Okay? With these terms, you hope that the theory is normalized. This is a physical argument, so consistency of the theory. But if you ask for phenomenology, you see our choice of lambda was large enough to have no compromise with experimental data.
No, but beyond this Laplacian term and beyond the choice of lambdas, there are, of course, other choices of.
Yes, of course.
This is what I'm saying. And these are not.
Oh, there are many choices. I mean, for instance, you can have no local term here, exponential of delta. Yes.
This is what I mean. Why restrict to these terms? Like these terms do produce non-perturbative.
I mean, yes, but the computation. I didn't show you the calculation. It's quite heavy. I mean, to compute for any n is not an easy task. So I hide it. But if you put this, what people call non-local actions here, putting some transcendental function of delta. By the way, one reason why we suspect that this theory is completely consistent is that if you consider lattice gauge theories, in the limit when A goes to 0, you have a series of continuous terms with higher derivatives, infinite series, not truncated like here. And this theory is rather positive. So it's unitary. So even if apparently you have those, you don't have it in the lattice formalism. The only problem in the lattice formalism is that you are breaking Lorentz invariance, whereas here you don't. So there are hints that tell you that it's possible to complete the standard model in a renormalizable way.
Okay.
This is the motivation.
Yes, I guess I was a bit confused because as far as I know, if you have some completion like string theory where you have infinite many higher derivatives, okay, these theories are well behaved and so on, the quantum gravity level and so on, but if you just truncate this infinite
But you don't have proof that these theories are asymptotically free in the UV.
Yes,
Okay?
that's true. But at least as far as I know, if you just truncate these theories to some finite degree,
Yes.
then you come back to the problems of unitarity and wrong signs and so on, and you're back to where you started, roughly.
Yeah, but yes, you're right. So here we could generalize this to put, for instance, here 1 plus delta parenthesis to power n. Then I will have a Newton polynomial of different degrees of powers of delta, right? The moral is that all of them are irrelevant for this one loop divergences. Only the leading one counts. This is a huge simplification. This does not explain what happens if you have an infinite series. Then you have to go to the very end. Yeah, we have not performed that calculation, but it's interesting, and maybe somebody should do it.
Thanks.
Sorry.
Just a real question. So, what about the inclusion of other fields like fermions or things? This is pure gauge theory, right? Have you considered that as well? Or?
Yeah, we have computed that. So they give the standard, because if you don't add high derivatives, the calculation is the standard one, which is on the books. So you just add it here. You change a little bit the coefficients of the one loop divergences. But I mean, it's very simple thing to do. And the result is that the domain of asymptotic freedom gets squeezed. If you put too many fermions, you destroy asymptotic freedom, even in A equal to 0. Yeah, you destroy. So to some extent, increasing n is like putting more particles on the game, on the model. So it's the same. You cannot put too many things, because then you lose asymptotic freedom.
Another question is, I mean, there are examples in quantum gravity, things like, the Reichert action, or which is not expandable because there is no scale, but there are people who put scales in this 1 over delta 4.
Yeah, I know.
I mean, is there any?
No local.
Is there some, you can think of this as the expansion or something local?
We are trying to escape from non-local things, yeah, as you asked. But it can be addressed too, but I'm a skeptic about the result concerning asymptotic freedom.
Well, I think saying the speaker. Yeah, I get it. Thank you very much.
Now, the important thing, which is the reception.
Well, the important thing is the reception. But still, what is